Welcome everyone to our introductory video on acids and bases. In this video, we are first going to talk about some observable properties of acids and bases, connect them to some everyday objects and substances. Then we're going to get into the theoretical definition for acids and bases, specifically the Arrhenius definition. Next, we're going to describe some of the chemical properties of acids and bases using the Arrhenius definition. Then we're going to look at the pH scale and then convert between the pH scale and the hydrogen ion concentration of a substance. Acids have been known about for many, many years, centuries, because acids are often found in common substances, specifically food products. That's where the word acid comes from. It comes from the Latin word meaning sour. So think of lemons, Sour Patch Kids, those sort of foods which have that sour taste. That sour taste comes from an acidic substance. Another property which has long been associated with acids is that they are corrosive, meaning they'll eat away at other chemicals if that substance is exposed to the acid. This can be used often to clean other substances, but it can also be a bad thing, is that if metals are often exposed to acids, it eats away or rusts the metal. Another property of acids, which you're definitely familiar with, is that they neutralize bases. Now, neutralization is a modern chemical term, but it's been known for years that if you add an acid to a base, the base loses its chemical properties. So this has been a chemical reaction which, even though the theory behind it was not known, we could still observe this happening on a macroscopic level. The word base is a modern term. The original term for basic substances is alkaline. And that is where those groups of the periodic table get their names. If you recall, group 1 and 2 metals, if they reacted with water, the water became more basic, or more alkaline. And so that was a property of those metals. And so those metals were given names related to the fact that they could produce a base. Now, if we think of some of our senses, bases have some common properties in that they are bitter and slippery. So by bitter, I mean the taste of like raw vegetables that are often somewhat unpleasant to eat if they're not cooked or don't have any salt or salad dressing on them, but they have that bitter taste. Bases also are slippery, and they can coat substances and so give them like a slippery feel. Bases, just like acids, are also corrosive. They can eat away at material. For example, Drano or any drain cleaner, the active chemical in that is a base. And so when it's exposed to whatever's clogging the drain, it eats away at that to free up the drain. And just like we talked about in the previous slides, bases neutralize acids. So if you add a base to an acid, it chemically destroys the properties of that acid, or neutralization. The theoretical definition of acids didn't come around until the late 1800s, early 1900s. It came from a Swedish scientist by the name of Svante Arrhenius. Now, he's a very interesting fellow because he was a really poor student, got very, very low marks, C's and D's throughout university, couldn't get a job anywhere. But he came up with this theory, which took a while to get accepted, about what happens when substances ionize in the presence of ions in water. And he really laid the basis for what we've been talking about when we've been talking about solutions and how substances exist in aqueous solutions. He ended up getting the Nobel Prize, I believe, in 1903. So he came a long way, but his theory for acids and bases is really the one that is most commonly used in introductory sciences and introductory in chemistry. There are some other definitions for acids and bases which are more appropriate to organic chemistry and when we're talking about equilibrium as well, which we will learn in grade 12 chemistry. But for this year, the Arrhenius definition will suffice. And according to his definition, an acid is just any substance which, when dissolved in water, produces hydrogen ions. So we can think of it like a chemical reaction. If we have some acid or some substance, HA, so that's just its chemical formula, and we'll use the letter A to just stand for the rest of the molecule. It doesn't really matter what it is. When it dissolves, the hydrogen breaks apart or dissociates from the rest of the molecule, and we get the production of hydrogen ions in water. It's the hydrogen ions in water which gives a substance its acidic properties. So this definition here relies on a few things. First, it relies on a substance being dissolved in water, so we have to have a solution here. Second, it relies on that chemical somehow having some hydrogen ions present, okay? And that's often how we've been recognizing acids in nomenclature, some number of hydrogens bonded to the rest of the molecule. An Arrhenius base is a substance which, when dissolved in water, produces hydroxide ions. So if we think of some chemical, BOH, where B is just often some cation or a metal. When that substance dissolves in water, it dissociates and releases the hydroxide or OH1 minus ions. Now, one thing to note is that it turns out that the hydrogen ion, which is just a proton, never actually exists in aqueous solution. As soon as an acid releases its hydrogen ion, that hydrogen ion immediately combines with one water molecule to produce a different ion called the hydronium ion, or H3O 1+. Chemists will often use the term hydrogen ion and hydronium ion interchangeably. From a chemical point of view, they're the same thing. One of the properties of acids and bases is that they are both electrolytes. And recall that electrolytes are substances which, when dissolved, they can conduct electricity. And from those previous equations that we've just seen, we can see why, in that acids and bases are substances which release ions, hydrogen ions for acids, hydroxide ions for bases. Soon as you have free ions in solution, then we can conduct electricity because the free charges can move from one electrode to the other electrode. Now, acids are mostly molecular compounds. And recall that when a molecular compound produces ions, that means that molecular compound has ionized. The covalent bond between the hydrogen and the rest of the molecule, in the case of the acid, has split apart. And so we now have free ions. Most bases are ionic compounds. So think sodium hydroxide, calcium hydroxide, potassium hydroxide. Those substances there are ionic compounds. And so when an ionic compound dissolves in water, it dissociates. The ions already break apart. So you'll see both of these terms used. We'll use the term ionize for acids and dissociate for bases. Another new piece of terminology is the difference between strong and weak acids and bases. I'll just be talking about acids here, but all of the same terms apply to bases and their meaning. A strong acid is one that ionizes completely in water. So what that means is if we put 100 acid molecules in a container of water, they would all split apart and we'd end up with 100 hydrogen ions. So all the water molecules release their hydrogen ions. A weak acid is one that ionizes only partially, which means if we were to put 100 acid molecules of a weak acid in water, maybe we'd only get 40 hydrogen ions, and some of those acid molecules would remain as full molecules dissolved in water, and they wouldn't ionize. Many of the acids that we commonly use in chemistry and in chemistry labs are strong acids: sulfuric acid, hydrochloric acid, nitric acid. Many organic acids and acids which are associated with food products, citric acid and acetic acid, which is the acid in vinegar, are weak acids. Many of you are familiar with the pH scale. A pH scale measures how acidic or basic a substance is. However, specifically, a pH scale is measuring the concentration of hydrogen ions in moles per liter. We'll get to that calculation in a minute. The pH scale is actually a logarithmic scale, which means that every step on the pH scale represents a 10-fold change in the concentration of hydrogen ions. So even though a substance with a pH of 2 and a substance with a pH of 3 seem close on the pH scale, there's actually a 10-fold difference in their concentration of hydrogen ions. The pH scale typically is listed from 0 to 14 because most common chemicals fall in that range. Substances which are neither acids or bases are referred to as neutral, and they have a pH of 7. As we move to higher and higher numbers, we increase in terms of how basic a substance is. And then going in the reverse direction, going closer and closer to 0, we become more and more acidic. As you can see, food products fall close to or just above and below the neutral range. And chemicals that we deal with in the lab are often more at the extreme ends of the scale, closer to 1, 2, or 13 and 14. Let's now look at a calculation for going from the concentration of hydrogen ions to the pH of a substance. Here's the calculation that we do for finding pH. pH is equal to negative log base 10 of the hydrogen ion concentration. Now, you might see this written with hydrogen ions or hydronium ions. It means the same thing. Now, these square brackets here might be something new that you haven't seen before. And a square bracket in chemistry refers to the amount concentration or the molarity of that substance. So pH is equal to the negative log of base 10 of the hydrogen ion concentration in moles per liter. We are shortly going to do an example of calculating pH, but most scientific calculators have a button that is either just written as log, or sometimes it will say log base 10. If it just says log, you can assume it's log base 10. That's the button that we're going to be using for this calculation. We're also going to be using the second function, in that the second function for that button on scientific calculators is 10, often written as 10 to the power of x. And that's going to do the reverse calculation that we'll need going from hydrogen ion concentrations back to pH. So let's take a look at that calculation first. If we want to go in the reverse direction, if we know the pH and want to figure out what the concentration of hydrogen ions is, we use this equation. Hydrogen ion concentration is equal to 10 to the negative pH. I find that the best way, which avoids most calculation errors, is by using the second function button. So the second function of the log button on most scientific calculators is 10 to the x, which is what we want. Okay, let's flip over to the whiteboard and do some examples here to finish off converting between pH and hydrogen ion concentration. For our first example, we are going to find the pH given the hydrogen ion concentration. Recall that we have a few symbols we can use for amount concentration. We can use the capital M. We can use the square brackets with the chemical that we're talking about inside. We also see C as well for concentration. They all mean the same thing. Our equation for pH is equal to the negative log base 10 of the hydrogen ion concentration. I'm going to switch over to an online scientific calculator so you can see the order in which I put in a logarithm in case you're not familiar with using that function before. So I'm using the Desmos online calculator, and every scientific calculator is going to be very similar. Sometimes there's slight differences in the order in which you find the buttons. So here I'm going to put negative. I'm using this as a minus sign. Sometimes you can use the plus minus sign on a calculator. Clicking over to function, I find my logarithm. And remember, on most calculators, it won't say the base of the log, but that's because the default is log base 10. So log, and I'm going to input my number, 0.0025, and press enter. And simple as that, I get a value for pH. We will typically express pH to 1 decimal, sometimes 2. The reason for that is because most high school chemistry class pH meters in which we'll be measuring this are not very precise. And so indicating a whole bunch of decimals is giving the illusion that we can measure pH to a level of precision, which we're unlikely to be able to. So we'll just typically stick to 1 or 2 decimals for pH. pH is dimensionless, which means there are no units to go along with it. So we just have a numerical scale. Let's now go in the opposite direction and find the hydrogen ion concentration of a solution with a pH of 10. This is a common problem that we need to solve in chemistry because we'll measure the pH and then we want to maybe do some stoichiometry with a question, and we need to convert that into moles per liter. So let's start off with the equation. So the equation for hydrogen ion concentration, if we know pH, is 10 to the negative pH. When this question gives us a pH which is a whole number, we can actually solve this without really using a calculator because this is really just a number in scientific notation, 10 to the negative 10. That's the same as 1 times 10 to the negative 10. So here we have our number, very, very small concentration. I want to highlight a few things though. This question gave us a pH of 10, which we know is, since it's above 7, that is a basic solution. Now, hydrogen ions, well, they are produced from acids. So we have a basic solution, and even though we have a basic solution, we still have a concentration of hydrogen ions. So this is something that we're going to explore in more detail. But a thing to note is that there's always hydrogen ions present, but just in bases, it's very, very small. Or specifically, we have a low hydrogen ion concentration. Just to illustrate some of the quantities that we're talking about in chemistry, I've added one more layer of calculation, which is an equation that we haven't used in a while, which is converting from moles to particles. So this number here, the hydrogen ion concentration, seems incredibly small, smaller than most concentrations we ever deal with. Yet if I take that concentration and say, well, if I have that concentration in 1 liter, how many ions are actually present? So I multiplied the moles, 1 times 10 to the negative 10, by Avogadro's number, the number of ions in 1 mole. And we find that even in such a small concentration, we have 6.02 times 10 to the 13 hydrogen ions. So that is still a huge number of hydrogen ions in a liter of water in what we consider a basic solution.